Good day, and thank you for joining us in this first podcast in our series on Applied Research in Photonics Incorporated, ARP, in discussion of its terahertz-based technology. My name is John Mahoney, president of C4 Technology, a sales and consulting company engaged in semiconductor, OEM electronic process and inspection tools. Today, we are joined by Dr. Rahman, President and CTO of Applied Research in Photonics Incorporated. Dr. Rahman is inventor of terahertz-based technologies utilized by ARP in the manufacture of nanotechnology enabling tools. Dr. Rahman, thank you for joining us today.
My pleasure, John. Thank you for the arrangement.
Dr. Rahman, in general, what is terahertz and why is it important?
So terahertz is the energy on the electromagnetic spectrum, like any other electromagnetic energy. The band between the infrared and microwave. It used to be called as terahertz gap. Now, like all other energy, when we express by their name, terahertz became a jargon or terminology because of the frequency in this range from some 0.1 terahertz to 30 or so terahertz. And this frequency draw attention of a lot of scientific community for more than one reason.
Okay.
One of the main attraction is that this energy is non-ionizing. So it does not hurt or perturb or damage delicate samples that that we need to probe with it. Therefore, and also the other thing is it is penetrating without damage. So it can penetrate through almost all materials except metal, where it does a few micron. But if we want to see or probe something below the surface without breaking it, then we can use this energy to probe under the surface, subsurface areas. But there are many other advantages of using terahertz. Another important issue is the sensitivity. So like X-ray can penetrate a lot of things, but X-ray has problem, it is ionizing, and it's not as sensitive as T-ray or terahertz. We want to call it T-ray because it makes a little bit of, kind of scientific connotation as opposed to pure engineering terahertz. So because of that sensitivity, terahertz started as the spectroscopy technique, and then we of course moved into the imaging area. So the sensitivity becomes important when we're doing spectroscopy. Spectroscopy is mainly getting the signature of some material, identifying it, or analyzing its properties in different ways. So FTIR, Rahman, they are very common tool. And FTIR, or fast Fourier transform infrared spectroscopy, FTIR. So the infrared energy is also used for probing, and it is very sensitive to bond vibration. So in a molecule where suitable bond will be probed by IR, it is very effective there. But there are molecules, so that gives a lot of advantage, but it has some limitations. And then particularly in molecule, there are so many other resonances other than bond vibration, which is sensitive. Terahertz is sensitive to all of them. Therefore, there is another advantage of using T-ray or terahertz. So these three are the main ones, but there are more, and we can talk about it.
Perfect. Thank you. So that's a great explanation. Can you tell us what industries and areas of science are really important to applied research and photonics technologies, and the impact that you might have on those? So what industries and science do you focus on, and where is the positive impact by using ARP technology?
Very good question. At ARP, of course, any effort is limited by the ability of a company, especially as a startup. But at ARP, we thought that a T-Ray application can go in many directions, but where are the biggest bang for the buck, so to speak? And problems remain in semiconductor industry and in biomedical industry that can be very conveniently and effectively attacked and solved by T-Ray approach. In semiconductor, they have, it's a metrology tool, so they can do all different kind of measurements. And having lattice scale resolution of ARP's T-Ray, we can see and measure and analyze the lattice structure of the semiconductors that are used. If there are lattice damage, we can measure that, quantify that. And also another important thing is the interface, because semiconductor is a many layer device. They put one layer after another and keep patterning it. So without breaking the whole device, or even breaking it, if something happened at the nth layer, it's very difficult to see and quantify that and measure that. Okay. And other things happen in semiconductor when you're putting one layer on top of another layer. There may be defect can happen. Inclusion can be included in there. Delamination can happen. Some other kind of imperfection can remain. So the interface analysis is another important thing in the semiconductor industry, which there are several different kind of interface happens when you put one surface on another surface. And T-Ray, particularly ARP T-Ray, we can see and quantify those kind of interface issues or lack of it. There are not always there are issues with the interface. So if it is not there, we can see that it is not there. If it is there, then we can see and quantify that. Other things in semiconductor are imaging the whole wafer is sometimes become important, as well as mapping their electrical properties, such as resistivity or carrier concentration. If there is any local variation or even depth variation, that kind of characterization is easily done by T-Ray as opposed to by any other technique. And also in semiconductor, failure analysis is another thing that can be done. But in the fabrication arena, they have a problem of yield issue. As you know, the value in a simple wafer may cost $200 to $300 or so, blank one. On that wafer, the fabs are building tens of thousands of chips or die, as we call it. On a 300 millimeter diameter wafer, there can be 10 to 12,000 chip on one single wafer. So the value then of that one single wafer turns from $200 to, on the order of $500,000 to $1 million when all the chips are packaged and made into device. Now, one of the issues that they are dealing with is the yield. To our knowledge, there are some 30% rejection of the wafer fabrication process. So if they are building 100 wafer, they are processing 100 wafer, 30 of them they cannot use for packaging. And the reason being that even though if it is coming from the same process, there is a little variation, and in that variation causes one die to be good die, another die next to it may not be the good die for packaging. So here the die and chip I'm using intermixingly, but die is the chip when still on the wafer, not separated and packaged. Die, when separated, singularized, and electrode attached and packaged, it becomes the chip. So die is the processed wafer pattern in a fab process.
So, Dr. Rahman, you've mentioned a few other types of technology, infrared. There are certainly in the very sophisticated world of semiconductor manufacturing, are there not many other technologies that can do what the applied research and photonics tools are able to perform? I would think that the industry has an established set of tools that can provide the measurements and inspection that the applied research and photonics tools are able to provide.
Absolutely. The industry is doing very well. We all know that. But then your question is also important. Why do we need another new tool? What's the problem that we are solving that they cannot solve? So first of all, the tools that they have in semiconductor industry, from the metrology point of view, uses most modern, semiconductor scanning electron microscope, atomic force microscope, transmission electron microscope, all different kind of spectroscopy, et cetera, et cetera. So there are still limitations. For example, there are more than one way of answering your question, but one of them is, how do we see things more clearly? The semiconductor chips work just fine, but yet they have 30% rejection. And for new processes, this rejection rate is much higher. So one of the things they do is when the whole wafer is done patterning, they use a multi-probe electrical testing for chips. And the industry has one of the way, they always want to increase their yield. That's where the money is. So how to increase the yield? They take the multi-probe electrical testing probe station and keep testing the chips, dies are still on the wafer. And when they have established a threshold, if the defective die number goes above that threshold, they would not bother with that whole wafer anymore. The cost of doing that way then becomes more than starting a new wafer. So when they reject a whole wafer, still there are a lot of good die on it that could have been used to add to the yield. So but the technology is not allowing them, because if they have to probe all 10,000, 12,000 die on a wafer, it will take long time, quote unquote forever.
And so some of the existing technologies that are used in the process, such as optical tools, which don't, and correct me if I'm wrong, don't have the ability to penetrate the surface of a wafer, those tools are still lacking the resolution and capability to see all of the defects that could occur during the various hundreds of process steps. So assuming that's all correct, and there's room for improvement in the metrology, inspection. Um, and terahertz has perhaps been around for some time, but not used in a way that applied research and technology is using, or perhaps there are other companies doing a similar thing. If there are, what differentiates applied research in photonics terahertz technology from the other terahertz technologies that may be available?
Wonderful question. If I may first finish the previous thought just for 1 second. So the fab yield is one thing. In other words, one of the distinguishing feature of ARP technology is that it can probe all dyes on a wafer in a reasonably short time, few hours, as opposed to few months would have been taken by the multi-probe technique. So once a non-good dye profile, the technique is called profile mapping, which is not a new concept except new application of T-ray, of creating profile of a non-good dye, and then on the fly it can probe all the dyes on a wafer and compare to the non-good dye profile, then number them as good or bad. So this way, each and every good dye will go on to the packaging, and that way it yields, go up. Yield will go up. The other distinct.
Are there not existing optical tools that can do a profile map? Are there optical tools that have that ability? And if they do, they could only really see the surface topography. Is that correct?
That's correct. And in profile mapping, we're not doing the whole image, which we can do in other applications. But in profile mapping, we came up with a criteria, is that when you make a T-ray profile of a single dye, it has a lot of intricate pattern in it that no other energy can see other than T-ray. So even if I am probing only one dye, that dye has so many different material arrangement in it and on it, within it. Therefore, only T-ray can see a lot of intricate material characteristic that neither X-ray nor IR nor visible light can see. So the advantage of that is that I have a known good dye, and that profile, a single line scan is a profile. That's the key. Because if I have to scan a lot of lines, then the time takes longer. But we have come up with a process where we make a single line scan, and this line can be on top of the wafer, in the middle of the wafer, the bottom of the wafer. That need to be determined. So there is a little bit of trial and error there. But once we know the profile of a known good dye, that is the standard, then we can scan all the dye on the wafer on the fly and compare and mark them as good or bad. And then the pick and place machine can come and pick the good ones.
Okay.
So I'm sorry, I missed the second part of your question.
Sure. If there are other, you've helped explain and differentiate between current optical tool capability and, say, profiling a dye versus T-ray. But if there are other T-ray manufacturers, companies available out there, what makes applied research and technologies T-ray technology different or better than say the competition?
Very important question. So the simplest way to think about it, there are two quantities that characterize a T-ray. So there are more than one T-ray source. We know that. The oldest one being the photo switch or it came to be known as the Austin switch after Dave Austin's name, who first demonstrated the T-ray from Bell Lab in the mid-80s or so. So two things that characterizes T-ray is one thing is the output power. How much power a sample can receive and reflect back or transmit through. So that's the source power, meaning that probe power. And the other one is the T-ray bandwidth. Bandwidth is something like a observation window, if you want to think it that way. With IR, we have a bandwidth of infrared. And so we have a window of infrared. Now, if we can expand that window, then we can see more things. So T-ray, as we generate our dendrimer dipole excitation-based T-ray, has a bandwidth of about 30 terahertz. So if some other source has 5 terahertz, then we have a 6 times bigger window. And this is important for spectroscopy. For imaging is also important. This gives us a much better sensitivity for seeing features. And of course, we can see lattice resolution with our T-ray, which is kind of, how can we see a bigger wavelength? We can use a bigger wavelength energy or radiation and still can probe the atomic lattice. That's another distinguishing feature of ARP's T-ray.
Okay. Thank you. And that's a big question. And of course, this is very complicated, but in summary, how do you take a large wave like T-ray and get sub-nanometer resolution? And of course, this isn't a quantum physics class, so maybe just a summary.
Sure. Well, as you mentioned, it's not a quantum physics class, it's not quantum computing or anything. We're still using the regular, desktop computers to do what we do. But so as far as imaging is concerned, diffraction limit is the limit for all imaging devices. And Ernest Avi established in 1873 that the smallest thing you can image with a microscope cannot be less than half the wavelength of the light that you are using. So invisible light, we have, if we use IR, maybe 800 or so nanometer near IR. Then according to Abi's diffraction limit, we can resolve 400 nanometer object with that. So that's far away from angstrom, which is the lattice dimension, atomic lattice dimension. So one of the thing is that as long as wavelength-based imaging is concerned, there is no way of avoiding the diffraction limit. So then what are the alternatives? And we came up with a technique, what we call is a wavelength decoupled imaging technique. In other words, wavelength is a form of energy. Anything is a form of energy. Light, heat, X-ray, gamma, everything is a form of energy. So if we can somehow separate ourselves from the wavelength aspect and stick to the energy aspect of it, then that gives us certain advantage. And the image formation then, is not wavelength dependent, but energy dependent. In other words, what we are doing here is we are taking our T-ray energy, which has a wide bandwidth. So you have smaller wavelengths and bigger wavelengths from few micron to millimeter. So it's pretty huge, but still even micron doesn't help us according to the diffraction limit. So our main premise is eliminate the wavelength dependence on image formation. So this is where we introduce our nanoscanner, and we actually scan an object with a nanometer or so resolution. And so in other words, when the scanning is done, it is nanometer resolution in the scanning. And then we have this computer algorithm to process that scanned intensity matrix, as we call it. It's a Beer-Lambert reflection matrix. And with that matrix, then we use our computer algorithm to form the image. It's not all that different from a camera. In a camera, you have a CCD. Reflected light is falling on a CCD or focal plane array, and that's giving the image like a all-day film camera. Still wavelength dependent, except in our case, we are doing that. Okay, instead of that CCD, we have a nanoscanner. We scan an object, then the reflected energy follows or can be explained in terms of the Beer-Lambert law. So, or modified Beer-Lambert's law. Therefore, we call it a Beer-Lambert reflection matrix. And that matrix becomes the input for the image processor, and it creates the image. So that's how we eliminate the diffraction limit.
Okay. Thank you. It sounds to me like any energy source could be decoupled from the wavelength if necessary. So why not decouple infrared from the wavelength and achieve the same results that you're achieving with your T-ray?
Right. That's another wonderful question and very valid question. So why T-ray? Why not visible light or some other mini laser or something? And so issue is if we want to see below the surface, then T-ray is important. Visible light or any other form, IR cannot do that. IR may still penetrate a little bit, but not all the way. As you know, we produce here volume image. By volume image, we mean that it actually has a X, Y, and Z dimension, 3D. Not just the surface texture, which have some depth, and we call it surface image or 3D image. It's quite different than having a simple surface 3D image than an actual volume image. So an user can go to certain depth as needed for that particular setup or particular experiment and create a volume image. So that's one thing only T-ray can do. I mean, X-ray penetrates, but X-ray has a lot of other issue. So X-ray is not a good way of doing it. It doesn't have the resolution and sensitivity, and also in addition, it gives the X-ray dose or perturbation to break the bonds, which is what we don't want. So that's one thing. The other thing is, as opposed to any other radiation, T-ray is the most sensitive radiation. So the reflection is happening or even transmission is happening. If the interaction is limited with the sample, then you get limited response, like in IR. But T-ray has a lot more interaction. Any resonance present in a molecule is sensitive to T-ray. Therefore, we get a lot better response from the material or sensitivity from the material. Therefore, we can see a lot of different features in our image.
And is that perhaps these different resonances you're talking about versus infrared, is that perhaps the difference between T-ray and infrared in the Rahman spectrum?
So the Rahman spectrum is a response to a material or sample where only bond vibration is giving that response. So if I have a big molecule and a small molecule ligand, something that there is a bond between two atoms, the bond vibration or resonance is sensitive to IR. Therefore, the Raman signature happens. However, if you think about simple water molecule, H2O, and if you look even in any textbook, there are so many absorbent peaks is theoretically possible. And yet, if you do the Raman spectrum of water, you will see one single peak. Where did all other go? The other are not there because of the lack of sensitivity. So because in water or any other molecule, there are bond vibration, but there's also other resonances like, in addition to vibrational, there's translational, there is rotational, there is torsional, and even conformational different, meaning that a same molecule with having the same number of atoms and same identical atoms in a different conformation. So all of these differences are there in a molecule. How do we see them? IR is not able to see that. Even NMR is not able to see that. NMR is a fixed frequency machine. So the T-ray is able to probe just about all resonances in there. I mean, which is a good thing and bad thing. I'm not saying that this is the silver bullet because it does have the highest resonance, highest sensitivity, but it also gives you so many absorbent peaks that there are not all the peaks can be explained. So there are a lot of work that need to be done for sure.
Sure. Well, it sounds as if the ability of T-ray to penetrate most all materials and the fact that semiconductor has so many layers and so many different materials and so many different structures and films that and in combination with the multiple vibrational states of materials, it sounds as if T-ray has the ability, and applied research in photonics technology has the ability to probe those inner layers where different materials meet and evaluate the structures as they come together, or in other words, the interface. Is that true?
Absolutely.
Okay. And of course, that is one of the most common methods of building a semiconductor. You have interfacing of many different materials, and I suspect that's where a lot of failures can occur. Well, Dr. Rahman, we could talk all day about this. I would like to schedule you for another podcast meeting where we could maybe dive into the specifics of some applications in semiconductor, perhaps biomaterials. I think one thing that may not be apparent in our discussion is that your method is non-destructive, non-contact, non-ionizing, has the ability to penetrate just about all materials without changing the material properties, which sounds to me like maybe this technique can be used in situ or during the process to measure what's going on in the process. And having read some of your publications, I know you've done a lot of work in kinetics experiments, and perhaps we can talk about some of that next time.
It would be my pleasure. And thank you for arranging this. Thank you for your time as well.
You're welcome, Dr. Rahman. Pleasure speaking with you, and have a great day.
Thanks. Talk to you soon again.
Bye for now.
Bye.